Welcome. Let's solve Leetcode 2017 grid game. All right, so let's read this thing. So we're given a zero-indexed two-dimensional array. So let's make that clear. Two-dimensional array of size 2 by n. Again, now this is the important part. It's only going to have two rows. Where each cell represents the number of points at position RC on the matrix. Two robots are playing a game on this matrix. Both robots initially start at 0, 0 and want to reach the bottom right corner. Each robot may only move to the right or down. At the start of the game, the first robot moves from 0, 0 to the bottom right corner, collecting all the points from the cells on its path. For all cells traversed on the path, it sets those cells to 0 once they've been traversed. Then the second robot moves from the upper left corner to the bottom right corner, collecting the points on its path. Note that their paths may intersect with one another. The first robot wants to minimize the number of points collected by the second robot. In contrast, the second robot wants to maximize the number of points it collects. If both robots play optimally, return the number of points collected by the second robot. Okay, let's go over this first example here. So we have this grid 2 by n, or 2 by 3 in fact, 254151 initially, and the red cells indicate the path of the first robot. Notice that after, in that case, well, sorry, this is just one path, and this is another path. So it's decided that, so this red path is the path of the first robot. And notice afterwards, everywhere, all of the red cells have been turned to 0. And this blue path represents the cell of the second robot. And so it gained a total of 4 points. And that's the expected return value. Okay, here's example 2. This is the red cells represent the path of the first robot. Notice after it traverses, it changes all of those cells to 0. And what's remaining is these other cells, 3, 1. So this blue path is the path of the second robot, and hence the return value is 4. Okay, they're all pretty much the same, so we can just kind of begin. Okay, so what's important here as we do this problem is we just need to figure out where it's optimal for the robot to turn, the first robot to turn. What I mean by optimal is we want to see how we want the minimum number of points collected by the second robot. So let's see that. Okay, so a lot of our computation will be based upon where the robot turns. So where the robot turns. Okay, so let's look at an example here. So suppose we have a grid like this, 1, 2, 3, 4, and then really the numbers don't count. They don't really matter. Okay, so suppose we're here. Now, we should first calculate, well, it makes sense to first calculate. Suppose the robot turns the very first cell. So don't worry about this here. So all of these dashes here, are these dashes? What are they? Underlines? Sorry. Well, these underscores here would be 0. So we should store this value here. And this would be the sum of the first robot. Okay? And then otherwise, well, now let's go the other way around. What if the robot does not turn there? So if the robot does not turn there, sorry, the first robot, we would have this scenario. we'd have this scenario. So we should compare these two. So the sum. So remember the second robot only has two options. First option is to turn immediately, and the second option is continue on until the end of the first row. So again, I hope that makes sense. So let's maybe go over this here. So the second robot can only go all the way to the end and down. That should make sense. Or it can go down and go all the way to the end from here. So it only has those two options. That would lead to the optimized value for the second robot. But the first robot is trying to reduce whatever the second robot does. Okay, so again, sorry, so let's continue on where I was. So suppose now the first robot decides to go here, and then maybe now it decides to turn. So what would be left with is comparing these two versus that. Then lastly, if it decides to go all the way, so that we'd be comparing these three cells to whatever came before it. Okay, so let's kind of go over that in code, and I'll go back to the demo and explain it as we go along. So what we should do is, so remember initially we had this, right? We had this, but the first option was when the first robot, sorry, not he, but the robot. So let's set up this situation. How would this look like? Okay, so what we'll do is we'll say the row 1 and row 2. So in a way, we'll be storing maybe like a prefix sum kind of and result. So this row 1 will continue. We'll calculate it, and it'll be everything. So it'll be the sum. Let's change this to a G here because I don't want to write grid. So the first row, and the second row so far would be 0, and the result we'll just set it to math.infinity. So remember, our goal is to do what? We want to return the number of points collected by the second robot. But the first robot wants to minimize the number of points. So the first robot is in a better situation because they get to determine where they turn. So they're in a better situation. So let's figure that out. So what we'll do is we'll calculate what happens when we turn. So we'll say for I in range, length of G0. So this is the number of columns. So what we'll do is we'll calculate turning at index 0, index 1, index 2, index 3. So we want to come up with this, I guess, calculation here. So what would this look like for robot 2? So robot 2 would be, so if we notice how row 1 is the entire row now. It's everything. See, it's the entire first row. So what we want to do is we want to remove the first element. So we can say row 1 minus equals G of the first row and this element. So now we've removed this element, and now we're just, so this row 1 is everything else. And now what we can do is we can actually calculate what robot 2 would have. So robot 2, we can say robot 2, let's go over this first. So equals the max of row 1 versus row 2. So what does these represent here? So remember, row 2 currently is 0, and row 1 is currently, well, row 1 in fact is just all these 3. So remember though, the second robot only has 2 options. It can go all the way from the first row and then go down, or turn immediately and then go across. So row 2, if we were to turn immediately and then go to the right, we'd have 0. However though, row 1 has these 3 elements not zeroed out yet. So that's what this represents here. It represents going all the way down, well, the row 1 score versus the row 2 score. And remember, row 2 has all these, they've been traversed already by the first robot, so it'd be 0. So we have that. So this would be like the current score for robot 1. Maybe we write that down. So temporary robot 2 best score. And well, but remember though, it's the job of robot 1 to minimize that score. So we can say if, well, let's do this here. Let's say the minimum of the result. Sorry. And we can just say here, this is the result. So now here, what we have here is, so this is trying to maximize the best score for robot 2, and this entire calculation is calculating the minimum score that robot 1 is trying to put upon robot 2. Okay, and now though what we can do is now we can adjust row 2 now. So we can say row 2 plus equals g of 0, g of 1 I. Okay, so well, what does that mean? So then, so suppose now robot 1 decides to turn at the next index. So here. So let's see. So row 2 currently has this value here. Row 2 currently has this value. But remember, row 1, well, currently it only has this. Remember, because we only took off the first one. But now let's assume we're in the second iteration. So in the second iteration, I is 1 now, so we can take this off. And now this configuration is, at this point, we need to subtract it. So that's what this does here. We've just taken this off. So now row 2, remember, currently has, from the previous iteration, has this one value added to it. So now we can perform the second comparison. So we can maximize this. So actually, let's print it out along the way. How about that? So we'll say return result. And what I'm going to say is, okay, I'm going to print out. I'm going to print out. So row 1, row 2. Okay, row 1, row 2. Now I don't know if that's, yeah, that should be okay. Row 1. Okay, that should be okay. And then let's print it out. And then let's print out this result here. Okay, let's print that out. Okay, so if we go to our first example here. Okay, so let's maybe make this bigger. Okay, cool. So row 1, so initially this 9 is here. Well, what does that mean? Remember, so if we traverse, if we turn down immediately, row 1 would be 9. That would be available left for robot 2 to use. And row 2 would just be 0. There'd be nothing there because first robot already took this corner. Okay, so this would be the scenario if robot 1 turned down immediately. Suppose though, on the next iteration, the first robot decided to turn down at this index. So what's left here is this 4. So row 1 has a 4 here. Now though, since the robot turned here, the first robot, if we wanted to, the second robot could use either the upper right corner or the lower left corner. And that's what that's what this 1 and 4 represent. Then finally, if the first robot decided to go all the way down to the end of the grid and then down, well, there would be this 6 here on the second row, this 1 and 5, and this, well, nothing available on the first row. That's why there's a 0 here. Okay, so I hope that helps. If it was unclear. And then that's it. We can just we can just comment it out for now and just return our result or submit our answer. Okay, looks pretty good. So I do have not much of an optimization, but more. I think I've mentioned this before in my other videos. Is that whenever we have this minimum and maximum taking place throughout the function, let's see if we can just remove them, because I think those are what I would call heavier than or more computationally intensive compared to a simple if clause. So what I mean by that is this: what if we extract some of this? Let's maybe take this out, put an R here, then we say if R is less than result, then we set result equal to R. Let's check if it works. And let's submit it. So it should be much faster because we're not, so you can tell it's much faster than our previous result. And okay, let's see if we can do one more. I'm not sure though how effective it'll be. So let's see, max row 1. Well, on this one, we don't really store. We want the biggest between row 1 and row 2. Now, we don't really store it outside of it. Let's see. We want the bigger of them. Yeah, I think we can leave it like this. I'm not sure if we try, because it may bounce, meaning it can go oscillate between which is bigger, row 1 and row 2. We don't really know. Okay, so I think this is fair. We want the bigger of these two, and we don't know which one is the bigger. We could do, I guess, maybe, I guess we could do this. Let me see. If row 1 is bigger than row 2, I guess we can do something like this. If row 1 is bigger than row 2, then we have row 1, else row 2. The thing is, we need to do that every iteration of the loop. I'm not sure this will help, but we can try. Okay, apparently it does. So yeah, my point stands is that if you can reduce the number of function calls, like minimum and max, then you will improve your performance, because there's a difference between, for example, always calling this function. You're always calling it, but the thing is, you don't need to always call the function. If you can do a simple if-else clause, it's much less resource intensive. So remember, let's look at our submissions here. Let's see. So at our submissions, I didn't change the algorithm at all. I only changed our usage of our implementation, the usage of the min-max function. So again, so I hope my point stands is that we don't. If you can, if you're looking for optimized code, the lower you go, the less, um, the less inclusion of external functions, then your code will be faster. However, like a lot of people like Python because of those easy functions and convenient functions. So again, it just there's a give and take between your goals and and your requirements. So that's something for you to figure out. Okay. Other than that, though, we should feel pretty proud. Our code is in the top 99 percentile, and we're up there with the top of the submissions. So good job. Okay, if you found this video helpful or educational, please consider liking or subscribing, or both. Have a great day. Take care.